Welcome back. So before we get back into our problems of finding volumes, I want to actually say one more really quick thing about finding areas of regions in the plane, because I kind of forgot to do this in my lecture on that topic. This is the problem with me trying to memorize all my notes and things ahead of time. Occasionally I forget one of them, but fortunately this is not too big a thing. I just want to make sure that I actually say it so that you know what's going on here. So one of the things, when we did regions in the plane, right, what I told you to do was, if we're looking for a region in the plane like this, where this is y equals f of x up here, this is y equals g of x down here. This pen is really awful. Let's see if there's a pen that is slightly less awful around here. That's slightly less awful, I think. But if I have a region like this, and let's say I'm going from A up to B, well, the way that we found this is we said that this is going to be, I can approximate this by splitting this thing up using these vertical rectangles. When I do that, I get a Riemann sum, and in the limit, it becomes the integral from A up to B of f of x minus g of x dx. Okay, that's great. That's everything we did. Now, what I want to point out, though, is that you can play this same trick using horizontal rectangles if you need to. So in some circumstances, you may want to actually use horizontal rectangles for your Riemann sum. And one reason that you might want to do that is, let's suppose that I'm actually dealing with this kind of a region. So what if I have two curves like this? Here's my, this is actually going to be like x is equal to f of y, and this is going to be, well, actually, let's call this one g of, no, this one can be f of y. And we'll call this one x equals g of y. Because in this case, see, you'll notice that these curves, they don't pass the vertical line test, and therefore y isn't a function of x. However, you will notice that x is a function of y here. Suppose now that I want to find this region in here, okay? I'm just going to put a little dot because I need to draw some other stuff on here, but I want to do this region. Well, I could try to break this thing up into vertical intervals, but doing so would be kind of annoying. I would have to, figure out, I'd have to break it up into this little piece here and figure out which part of the curve is on top. I'd then have to do this little segment in here, and here would be my top curve, here's my bottom curve. Then I would have this third segment or sector over here with a top curve and a bottom curve. And even just trying to write out what is the top curve, what is the bottom curve as a function of x could be really annoying depending upon what this thing is, okay? So what I can do to try to fix that is I can say, since I have reasonably nice functions expressing x as a function of y, what if I just instead break this thing up into horizontal rectangles? And let's say that we're going from A up to B here. Well, if I break this thing up into horizontal rectangles, I can play an identical game with Riemann sums like we did with the vertical rectangles, okay? It's literally the same thing. The only difference, and this is literally the only thing that changes, is that the x's and the y's get interchanged. So what I end up with is this sum from I equals 1 up to n of the right curve. Notice that f is on the right here, and notice that g is on the left. So I take the right curve, f evaluated at yi star, minus the leftmost curve, g evaluated at yi star, and that is multiplied by b minus a over n. That gives me my approximation, and as n goes to infinity, this approaches the integral from a up to b of f of y minus g of y dy. So we can find areas in the curve by integrating along the y-axis, and in some cases that's going to be more convenient than doing it along the x-axis. It's really just a question, and here's how you decide which one is more convenient. The question is it easier to describe the heights of vertical rectangles, or is it easier to describe the width of horizontal rectangles? Because that's what you're really integrating. you're either integrating the heights or you're integrating the widths. And so if I can describe the heights in a very convenient sort of way, well, then I want to go with that, and I want to integrate the heights along the x-axis. If I can describe the width in a very convenient way, well, then I want to actually integrate along the y-axis and do the widths. To give you an example of this sort of thing, let's suppose that I want to find this region here. So let me draw a little picture. Okay, this pen also sucks. Wow, I don't have any good pens in my office right now. Clearly, I need to go find some new pens somewhere after I finish this video. But I don't really feel like running out. Okay. Oh, a working pen. Okay. So here we go. Let's suppose that I want to do this region. I have 1, 1, and then this is going to be the curve y equals square root of x. And I actually want to do this region in here and find that area. Well, I could do this using heights. And the heights here, this top curve is just y equals 1. So I could set this up as the integral from 0 to 1 along the x-axis of 1 minus square root x dx. And that would give me the area. But it might be easier to notice that this curve is actually x is equal to y squared, as y goes from 0 up to 1. And the width of one of these rectangles is just going to be y squared minus 0. So I could do the integral along the y-axis of y squared minus 0 dy. Now, both of these are feasible for us to do. We know how to integrate both of these things because they're both relatively simple. You know, you turn this square root x into an x to the 1/2, and then you just use the power rule for antiderivatives. But this is a much easier integral, as I think you'll agree, okay? So either one of these will give me the same answer, but this is definitely the easier one to do. And in some cases, it might be way easier for me to do this integral along y. For instance, supposing that I had something like this region. So let's say that here's 1, 2, and I gave you something like, okay, this curve, and let me make sure that I actually write this out the way that I want it to be. So let's say this starts here and it goes like so. This starts here and it goes like so. And I tell you, okay, this is the curve x is equal to sine y plus 1. And this curve over here is x is equal to 1 minus sine y. Well, it would be a royal pain to try to describe the rectangles in terms of the top and the bottom here. Be well nigh impossible, quite frankly. But the widths of the rectangles are actually very, very simple, right? In order to figure out what is the width of one of these rectangles, well, it's just sine y plus 1 minus 1 minus sine y. And so what I can do is I can set this up as the integral from 0 up to pi of sine y plus 1 minus 1 minus sine y. All of that has a dy on it, and that just becomes the integral from 0 up to pi of the ones cancel, the signs combine to give me 2 sine y dy. So in this case, it would be like, it would take me like 20 or 30 minutes to even figure out what I'm supposed to, okay, maybe it wouldn't quite take me that long, but I'm not even sure off the top of my head how in the world I would describe the heights of the rectangles here. But if I want to do it horizontally, then it's actually fairly straightforward in this case. And of course, at this point, we know the antiderivative of sine is negative cosine, so we're kind of all set here. We can do this integral. Now, that covers dealing with areas in the plane, but this actually kind of segues nicely into what we're doing today in terms of finding volumes, because let me explain why this is actually related to what we're doing today. Also, excuse me, felt I did have to sneeze. Okay, there we go. Excuse me. So, let me show you why this relates to finding volumes in a certain way. The way we were finding volumes of revolution last time is we would take our axis that we were spinning around. So we had some axis of revolution, and the axis of revolution, we would give coordinates. I think I used the letter T so that I wasn't specifying whether this is the X or the Y axis or maybe something else entirely. And then what we would do is we would say, if I have some curve here where we have the radius of T, like the radius as a function of T, and we're going from A up to B, and we spin this thing around this axis of revolution. Again, this kind of gives us this spinning a pot shape. Well, the way that we were doing this is we used the method of washers or annuli or discs, depending upon how you want to talk about it, or even some people call it the method of rings. We said, okay, let's try slicing this thing up into thin slices. Each of these slices is A, hard for me to draw, but B, we know how to find the volume of it because the volume of the cylinder is just the area of the end cap times the height, or in this case, times the width. So we then integrate the area of the cross-section along this thing. The cross-section just refers to what you get when you slice a three-dimensional object up, right? So if I take a slice straight through something, that is its cross-section. And we integrate that cross-section area from the one end of this pot to the other end of this pot, so to speak. Now that works fine, except when it doesn't. Except when that's really hard to do, in other words. So in theory, you could always do this method. In practice, what you might end up with is an integral that is well nigh impossible to do. And in that case, there might be a simpler way of thinking about this. And I want to show you that simpler way. Well, it's not always a simpler way, but something that can be simpler in some other cases. So let's think about what would happen if I draw my axis of rotation like this. And then let's suppose that I have a curve. I want to draw something that's reasonably simple here so that my artistic abilities aren't too challenged. So let's say that this is my curve that I'm going to be spinning around this axis. And so let's suppose, in other words, we are rotating this region around in order to get some sort of a region. I'm not going to label those for now. I know I put a label there, but I really shouldn't have. That's not quite what I wanted to do. So in this case, what we get is something that looks a little bit, well, it looks sort of bowl-shaped, except it doesn't have a dip in the top. You'll just have to kind of go with what I've drawn here, hopefully. So we're taking this region and we're spinning it around. Now here's the thing. The heights of the areas of the cross-sections, if I just chop this thing up using cross-sections, that might be rather complicated. Actually, let me make this just a bit simpler for us. And for this example, we're going to take this all the way in like so. So instead of getting that kind of shape, we're going to end up with a full bowl shape. And there's a reason why I want to do this. If I just tried to slice this thing up, that might end up being somewhat tricky to do, depending upon what this curve is and how I can describe it. But there is another way to approximate the volumes, and that's really the important thing here. So there's not just one way to kind of approximate a volume. There's actually a number of different ways of doing it. In fact, there's more than just that way and the way I'm going to show you today. There's many other ways of doing it, but these are the two that are sort of the most straightforward usually to deal with if we're talking about a volume that you get by rotating a curve or a region into 3 dimensions. So what if, and let me erase this shading of this region so that we have a little bit clearer thing to work with. What if instead of trying to slice this thing perpendicular to the axis of rotation, what if instead I were to use cylindrical shells? In other words, what I'm going to do is I'm going to take a little cylinder that runs around this entire thing. So there we go. I take this cylindrical shell type thing. Think like the shape of a pipe. So it's a hollow cylinder here. And what if I try to approximate this volume by filling this thing up with cylindrical shells? Well, the volume of a cylindrical shell is something that we can compute. And I apologize, I'm trying to write this down and I'm not very fast with writing. So to compute the volume of a cylindrical shell, how do we do it? Well, the basic rule is it is the area of this ring around its base times the height. And the area of the ring is going to be, well, it is the pi outer r squared minus inner r squared. Okay, so that works out okay. And then we want to multiply by the height. So we get pi times r outer squared minus r inner squared times the height. Now, what ends up happening is when you write down the Riemann sums for adding up all of these cylindrical shells, in the limit, the Riemann sums we get are going to approach an integral, but the integral that they approach is going to be not quite exactly necessarily what you might expect, because you see it's going to approach this thing where as we take the limit, this actually turns into the derivative of r squared. It doesn't just remain as r outer squared minus r inner squared. What it really approaches is 2 pi times the radius, because in the limit, as these cylindrical shells get thinner and thinner, what's going to happen? Well, the difference between the outer and the inner radius is going to approach 0. But we are multiplying by one of these widths here. So it turns into a derivative with respect to r. And so what we get is we get the integral from 0 out to whatever the full radius is here of 2 pi r times the height as a function of r, where the height here is the height of the cylinder given as a function of our radius away from the axis of rotation. And we integrate this radially. So radially meaning that we are integrating perpendicular to the axis of rotation. And so this gives us another way of finding the volume. Now, I'm not going to show you every single detail of how that turns out. It's kind of just a weird technical computation. And if you are really interested in seeing the full computation, you can take a look in your book and see all of the details in there. I think for now, maybe it's better to just kind of talk about when would you use this, how would you use this, what is this good for, and kind of compare this to the way that we did things using the slice method, the slicing things into discs or annuli, also known as washers method that we talked about in the last lecture. So let's look at an example of doing this kind of thing. Let's suppose that I want to find the volume of revolution for this region rotated around the y-axis. So we're going to go with this. This is y equals x squared, and we're going to rotate this region here. So what is this going to actually end up giving us for a shape? Well, the shape is going to look like a vertical cylinder, except that it has this parabolic dish cut out in the middle of it. There's actually good reasons why you might want to make something like this in real life, okay? There's, I don't know if you guys know this about parabolic dishes, but parabolic dishes have the property that if you have a bunch of incoming rays that bounce off of the parabolic dish like a mirror, they all focus to a single point along the central axis. And for this reason, they're really useful for making things like satellite dishes or radio detection dishes. Those shapes are not arbitrary, and they're not anything weird. When you see those dishes in real life, they're actually parabolic in shape. And the reason is because all of the incoming rays of radio waves or satellite waves, whatever it is we're talking about, satellites, I don't know what frequency they use, but whatever frequency they are using, they're all essentially coming in parallel to each other, and they will all get focused by this parabola down to one point. So if we just set our antenna at that point, it's actually as if we had this huge antenna that takes up the entire parabolic region that we've covered, okay? So all of those rays come down to the one point of the antenna. So that's why we might want to build something of this shape. That's kind of irrelevant to the problem at hand. I'm just figured it's interesting to see that, yeah, we're not just doing arbitrary examples all the time. Some of these really do relate to some things in the real world. So when I rotate this around, I get a cylinder with a parabolic thing drilled out of it. Of course, normally maybe if we're just making a parabolic dish, we would put another, we wouldn't leave the entire corners of the cylinder on here because we'd want to save material. But anyway, so what is the volume going to be? Well, I could try to do the slice method. And if I did that, I end up with this kind of a shape here that I cut out. But if I tried to do the slice method, it's what I would call possible but annoying. This is something that we encounter rather frequently, actually. Things that are possible but annoying. And the reason for it is because the outer radius isn't too bad. The outer radius would always be 1, but the inner radius would have to be given by thinking about this as x is equal to square root y. So we'd end up with like this integral from 0 up to 4, because that's along the y-axis of, actually, I take back what I said about this being annoying. It's really pretty straightforward in this case. 1 squared minus square root of y squared dy. Okay, so this one isn't so bad, but I still want to illustrate how you can do this using the cylindrical method. I'll show you one where it's much worse in a moment, where we really do need to use the method of cylinders. So, alternately, what I can do is I can use the fact that the height in the radial direction, and the radial direction in this problem is given by x, the height is given by y. So the height as a function of x is going to be given by y equals x squared. And then what I do is I just do the integral from 0 to 2, because, I've gone out to 2 here on this particular region, of 2 pi times the radius, which is x, times the height, which is x squared, and I integrate that in the radial direction. So in this particular instance, both of these are fairly straightforward integrals. I was thinking this one came out a bit messier, but it actually isn't so bad. But we can see here that there's these 2 different ways of doing it. Now, which one do you want to use? Well, the question is really, is it easier to describe the radius of a slice, or is it easier to describe the height of a cylindrical slice? Which function is simpler to work with? So let me show you another example here where there is a clear winner, and the clear winner is going to be the cylindrical method, I think. So let me suppose that I want to do the same, but for this region. And let's also close the door, because I don't know what in the world is making that ruckus in the hallway, but I don't want you guys to have to listen to that so loudly. So let's suppose that I want to rotate this. Y is equal to cosine x around the y-axis. Okay, so the problem is that if I wanted to do this by the method of disc slicing, I would have to slice this thing up. So I would have to think about, how do I rewrite this in terms of, well, x is going to be a function of y, but it's going to have to be written down in terms of an arc cosine or an inverse cosine. Now, we could handle that, but it's kind of annoying. So I'm not saying it's totally impossible. I'm just saying it's not really easy. It would definitely be pretty tricky here. However, actually, it might be impossible because then we have to square the arc cosine. Yeah, so if I tried to do the slices, the radius here would be like x is equal to, and see, it's not even just the arc cosine. It's something more complicated than that. Well, yeah, I guess it is just the arc cosine, isn't it? X is equal, yeah, it's just x equals arc cosine y. However, we would then have to square it, so we would end up with this integral from 0 up to 1 of pi times arc cosine squared x, or y, dy, and I'm just worrying here whether I need to put it in a negative, but I don't believe I do. See, this is where things get tricky when you're dealing with arc cosines. Because cosine is not one-to-one, you always have to be careful when we try to reverse things that we're actually making sure that we shift everything by the right amount. Anyway, the point is, yeah, I'm reasonably confident here that this is correct. And the point is, I didn't think much about this when I was preparing this, because this becomes an ugly nightmare. I don't know how to do this off the top of my head. In fact, I don't even know if this is possible to do. I would have to spend some time trying to figure it out. Like, clearly, this integral does exist, but it may not have a nice, what we call, closed form expression. I don't know if I can find the antiderivative to arc cosine squared and write it out in terms of the functions that we usually work with. So this would be awful. Perhaps impossible. Perhaps not just awful. Perhaps it's really an impossible thing to do. Fortunately, if we do the cylinder method, it's going to be really, really easy, because the height of the cylinder is just going to be the cosine of x. And then I do the integral from 0 up to pi of 2 pi x times the cosine of x. Now, this looks like it might be quite difficult to do. And for now, we don't really quite know how to do this problem. It's true. However, it turns out that, yeah, we can actually do this integral. So we will see soon, this is actually quite straightforward. So in this case, what we end up doing is we use a little technique called integration by parts. It's sort of like doing the product rule in reverse. And it turns out that, yeah, it's actually very easy to do this integral, although maybe it's not quite obvious how to do it yet. So this is a situation where we can use the cylindrical method to write down a reasonably simple integral that we are able to do. Now, again, we can do the cylindrical method with things that are being rotated around any line that we want to. So, for example, if I wanted to use cylinders to find the volume of this region rotated around y equals -2. So let's suppose that this is what we're working with here. And let's suppose that the region that I have is going to be given by this. So let's suppose that it is given by this is the line y equals x, and then we're going to have, let me make sure that I actually do this correctly here. X equals 4 minus 1/2 y squared. And so I'm going to take this region and I'm going to rotate it around the line y equals -2. Now, I could do this using the method of slices, but if I did it with the method of slices, I would have to go from 0 to 2 along the x-axis, and then I would have to go from 2 to 4 along the x-axis, and also this part along the x-axis. Well, it wouldn't be impossible. It wouldn't actually turn out to be super horrible, but we'd have to break this whole thing up into a bunch of pieces. If we do the cylinder method, then it's fairly easy, because now all I have to do is to write down the height, and I need to think about the radius. Now the radius is going to be the distance between one of my cylindrical pieces and this y equals -2 line. So here's where we want to be careful. The radius in this case isn't just going to be the y variable, it's actually going to be the y variable plus an additional 2. It's not simply going to be y. So the radius here is equal to y plus 2. And this is why you got to be careful when you're doing these methods if you're not just going around one of the standard axes in the coordinate system. The other thing is that the height, this also means, by the way, that y is equal to r minus 2. The height as a function of y is going to be, the height is really going to be this distance here. And as a function of y, it's going to be the right-hand curve minus the left-hand curve. So 4 minus 1/2 y squared minus y. Sorry, I was worried I was blocking the camera for a moment. So that is going to be the height as a function of y. But actually we want to write this as a function of r. Y is actually r minus 2. So the height as a function of r is going to be 4 minus 1/2 r minus 2 squared minus r minus 2. That's 4 minus, 1/2 r squared, and then we're going to have -4r times -1/2 is plus 2r, and then -2 squared is 4 times -1/2 is minus 2. So then we have another minus r and a plus 2. And so that becomes 4 minus 1/2 r squared plus r when we simplify everything down. So that is our height as a function of the radius, and then we are going to be integrating from a radius of 2 up to a radius of 4. And that's all we have to do to set this thing up. So let me erase this top here so I can write down the integral, and we can write this as the integral from 2 up to 4 of 2 pi r times 4 minus 1/2 r squared plus r dr. And now you multiply through, you've just got this nice polynomial antiderivative to do, and you're pretty much all set. Once again, we could probably have worked this out by using the method of disks instead of the method of cylinders, but I wanted to illustrate how to do this with the method of cylinders. Also, another way that I could have done this is keep this in mind. I'm going to have to erase this for a moment, but keep in mind what I've said here. So an alternative here would have been to leave everything in terms of y, but remember that r is y plus 2. Now the height with respect to y is 4 minus 1/2 y squared minus y. Then what I could have done is I could have said, okay, we're integrating from 0 up to 2 along dy. But for the 2 pi r, I now have to do 2 pi times y plus 2. This in here is my radius. And then I can put the height as a function of y, like so. So this gives me something that I would have to then multiply everything through. Again, though, it just turns into a nice little polynomial integral that we can deal with. It's nothing particularly nasty here. So this shows us how we can do, whoops, I erased my y equals -2 line here. This shows us how we can handle this situation by using cylinders. So here's the question that people usually have. When do you want to use cylinders and when do you want to use slices? Well, they're both forms of slices, right? But when do we want to slice things into cylindrical shells versus slicing them into discs or annuli? And again, here's what you want to ask yourself when you approach a problem. In this region, how easy is it to find the radius as a function of height and square it versus how easy is it to find the height as a function of the radius and multiply by the radius? Because it really depends which of these comes out to be simpler. Is it easier to work with pi times the radius as a function of the height squared versus 2 pi r times the height as a radius of r? Which is going to be easier to integrate? So this is going to be integrated with respect to dh. This is going to be integrated with respect to dr. Which of these integrals is going to be simpler? That's the question that we have to ask ourselves whenever we approach this. Unfortunately, there's no hard and fast rule here that I can tell you, oh, these are always the situations where you want to use this guy, and these are always the situations you want to use this guy. Sometimes you will immediately kind of look at it and see, oh, it's very easy to write down one of these formulas and integrate it. The other one, we don't even need to worry about. Like if you just see, I can do this, you might want to just do it and not worry about it. If you just see that you can do the cylinder method easily, you might want to just do it and not worry about whether the discs work. But sometimes it's kind of tricky, and then you might want to try messing around with both of them. The good thing is that as you gain experience with doing these problems, you will find yourself recognizing patterns where, oh, in this situation, it's easier to use cylinders. In this situation, it's easier to use annuli or discs. So these are the considerations you have. Other considerations you might want to think about are, is it easier to find the bounds for the height? Because remember, this goes from like the height at the bottom of the region to the height at the top. Maybe you get particularly ugly bounds for that you don't want to mess around with. This goes from the inner radius to the outer radius of this thing that you're spinning around. So that's another consideration, but I would say that's usually a secondary consideration versus how bad is it to actually just do these antiderivatives. So as you practice these, try to always keep in mind which one is easier, which one is harder. And at least one of the problems on your homework is going to ask you to do this problem, or the problem that they give you. It's going to ask you to find a volume using both of these methods. And then you can kind of think about, okay, which one was easier in this case? And why was it easier? And what can I use? Like, what does that tell me about when one method is going to work better than another? But this is the kind of thing that you're going to have to kind of play with a bit yourself to get a feel for it, rather than just me telling you, here's the rules for what to use. Now, is there anything else I want to say about this? Oh, yes, of course. Okay, so what I wanted to say is, in addition to reading stuff in your textbook this week, I have given you guys some supplemental reading assignments to work with from Paul's math notes, dealing with finding volumes of revolution using the annulus method versus the cylindrical shell method. And I did that. You don't have, I mean, you're not obligated to read this stuff, okay? It's not like I can force you to do it. But I'm giving you that because I think it will really help you to see these additional examples. These are long examples sometimes to work out from start to finish. And so there's kind of a limit to how much time I want to make you spend just sitting there staring at me. But having these examples written down for you that you can kind of refer to at your leisure and work through at your own pace is a really good thing. The other nice thing is that his website even has practice problems that you can try yourselves. If you click, there's like in the navigation bar that on his website, there's like notes, practice problems, and assignments or something else. I don't remember the exact wording, but you click the practice problems and it will give you problems that you can try out step by step. So I'm going to say, with something that is this kind of tricky to get a handle on, spend some time reading his examples and trying out the practice problems. Since he's already done it, I figure there's no reason for me to kind of reinvent the wheel by doing it myself, since he's kind enough to post all of this online. But of course, if you have questions about anything that you're reading, then please feel free to come see me or email me or whatever, and we'll talk about them. Okay, so these have been examples this week of using integrals in situations where we're not just integrating a function, where we're actually trying to find some quantity. Generally speaking, the way that we've done this, remember, is we wrote down a Riemann sum to approximate some quantity, whether that was the area of a region, whether that was the volume of a region. We figured out a way to approximate it with a Riemann sum. We take the limit of the Riemann sums, and once we have the limit of those Riemann sums, we say, okay, that turns into an integral. And that's really just a trick that we can play pretty much whenever we want to. Well, anytime that we can approximate something with Riemann sums. So next week, we're going to continue seeing how that works in the situation called work, actually, a topic that kind of comes from physics. In the meantime, I may post one more very brief video this week, but we'll see. Probably I'll figure that out later. In the meantime, this should be enough to do everything that you need for your homework. So I will see you guys later.